Decades ago, running a computer program meant installing it directly onto physical servers. We're talking about massive mainframes taking up entire rooms. Physical machines lacked strict boundaries between programs. Put two applications on the same server, and one greedy program could gobble up all the memory. The second application is starved of resources. It sputters, slows down, or crashes completely. To fix this, companies bought a brand new physical server for every single application they ran. It was a simple, blunt way to keep them separated. Maintaining a 1-to-1 ratio between hardware and software was wildly expensive. Most of the time, those servers only used a fraction of their processing power, leaving massive amounts of expensive chips completely idle. The solution was virtualization. Engineers figured out a way to take one physical server and carve it up into multiple independent virtual systems. This meant you could put different applications on the same physical hardware, but keep them isolated in their own virtual boxes. An application in one box couldn't peek at the data or steal processing power from another. This improved hardware utilization, reduced physical costs, and made updating applications much easier. A single physical machine could now do the work of 5 or even 10. But these virtual machines carried a hidden weight. To make them work, every single virtual box had to run its own heavy layer of software, a complete operating system, just to support the tiny applications sitting on top. Virtualization successfully eliminated the waste of physical hardware. However, it replaced it with software bloat, forcing computers to waste energy running dozens of identical, heavy operating systems side by side. Modern developers needed a way to shed that weight. They created containers. Think of a container as a much lighter version of a virtual machine. Containers share the computer's underlying operating system instead of bringing their own. This makes them incredibly lightweight while keeping independent memory and processing boundaries. Because of this separation, they are highly portable, moving seamlessly from a private office server to a public cloud. Developers can quickly build and test a software update on their personal laptop, and they can completely trust that it will behave the exact same way when it goes live for millions of users. From an operational standpoint, this allows systems to run far more efficiently. Large, complex programs can be broken down into smaller, individual containers that connect together smoothly, making it easier to isolate issues or update specific pieces without taking the whole system offline. By stripping away the heavy operating system layer of older virtual machines, containers transformed software applications into efficient and portable building blocks. But this created a new logistical puzzle. When you have thousands of individual containers running a major website, you need a way to manage that massive fleet and guarantee the site never goes offline. If a single container running the checkout page on a shopping site suddenly crashes, you can't wait for a human to notice. You need a system that immediately detects the failure and instantly spins up a replacement. That system is Kubernetes. It is an open-source platform specifically designed to automate all the heavy lifting of managing, scaling, and repairing these large networks of containers. It is helpful to understand what Kubernetes does not do. It doesn't write your application code. It doesn't provide built-in databases or force-specific monitoring tools. Instead, it acts as a constant supervisor. You provide it with a blueprint of your desired system, like always keep 5 checkout containers running. Kubernetes then works like an automated checklist. It continuously looks at the current system, and if things don't match your blueprint, it makes the necessary changes to fix them. The name Kubernetes actually comes from a Greek word meaning helmsman or pilot. It doesn't do the rowing itself, but it continuously steers your fleet of containers to keep everything stable and online. Let's look at exactly how it steers that fleet. When a massive surge of visitors hits, Kubernetes acts as a traffic cop. It evenly divides network requests across active containers to prevent overload. During software updates, it swaps out old containers one by one without interrupting service and automatically attaches required digital storage. It also acts as an incredibly efficient packer. You tell the system how much memory and processing power each container requires, and Kubernetes intelligently fits them onto your available server firmware to ensure no space is wasted. If a container stops responding or fails a health check, its self-healing mechanism kicks in. Kubernetes will instantly kill the broken container, start a fresh one, and hide the whole process from your users until the new container is ready to work. It securely stores sensitive information, like user passwords and security keys. You can update these hidden credentials across your entire system without needing to rebuild any of the underlying software. Beyond that, it manages background tasks, scales your application up or down automatically based on how hard your servers are working, and assigns precise digital addresses to every piece of the puzzle. By combining over 15 years of lessons learned from running massive operations, Kubernetes provides the framework needed to run resilient, automated systems at any scale.